All right, I think we're gonna carry on here. Yeah, so I guess just to set the stage a little bit for guess where we're gonna go into for the next rest of today and tomorrow. It's gonna be, I think, a bit of a change in perspective, maybe a change of pace between what Alex has been doing. So Alex has he's got a lot of like really fantastic experience, having worked for a manufacturer, having worked for a utility, and now, being heavily involved in the standard development work. So he's got sort of like a really huge wealth of experience in terms of understanding the context of these topics and EMT and IBRs and these things. For myself, I'm going to be speaking more so from a studies engineer perspective, which has been my whole career. So I've worked for a consultant for the past 10 years, and we've been, kind of in the trenches of EMT studies, EMT model testing, and so I'm going to be speaking more from that perspective, and getting a little bit more into the nuts and bolts on how you actually go about performing these model testing, how you go about performing EMT studies. So I think this is going to be, I'm going to be touching on some low level things in terms of some details, let's say, in terms of how you go about doing these things, but also hopefully it's going to have aspects of the content is going to be really useful for folks who are more in the managerial level and helping to sort of guide the process a little bit as well. So I think there should be something for everyone here. Yeah, as Alex mentioned, feel free to interrupt at any time if you have questions on what I'm talking about here. If I'm not making any sense, just let me know and we can back up. And just to note on some of the content here is going to be, like I'm going to have to show you, we're going to be getting into the tools a little bit as well here, right? I'll say that everything that I'm going to present is more, based on my experience, based on the workflows that I'm used to in our shop. But a lot of these things can be done using a different process, different tools, let's say, different EMT platforms and different translation tools and things like that. So just to note that, I am biased because of, my experience and my specific situation, but I think that the principles of what we're going to share is going to be transferable to whatever situation you guys are dealing with. So just a note on that before we get started. So yeah, my plan for today is really kick things off with an IBR controls review, and we'll talk about why that may or may not be important for you, and then we'll sort of from there we'll pick up where Alex left off on the sort of model intake and testing or design evaluation item, and then we'll go into EMT system model development, and we'll see how long that takes us. And if there's time left, we'll move into special studies already, but I suspect we might not have time, but let's see. And yeah, one more item. Just 1 second. That out later. Normally, like we teach a lot of courses at electronics. They're generally more hands-on courses where we'll be, like doing a lot of button clicking in using the tools. We're going to be pretty light on the hands-on aspect. Of course, you all can just follow along on the screen here. No need to try anything on your own here. But just to know that this is fairly different than the type of course that we usually teach on EMT, which is more implementation heavy and walking through the actual like minor detailed steps. And I'll be providing hopefully more of a high level perspective on these studies and these tests here. So yeah, all right. With that said, let's carry on. So yeah, so IBR controls. I think a lot of you are going to be really familiar with a lot of these notes I'm going to make here on controls, but And from one perspective, you could say, okay, why do we need to know exactly how the IBR controls are going to work? We have our performance requirements, we have our standards, and maybe that's all we care about. But when you're actually going through the details of these processes, it's very helpful for you to understand the expected behavior of these devices. It's very helpful for you to understand the nature of inverter-related instabilities, which are very much tied to the typical control structures of these devices. And it's very helpful when you're diagnosing and debugging EMT model issues to understand how they actually are supposed to work. And if you want to talk the same language with the OEMs, the expertise who are actually supplying this equipment, then it's also very helpful to facilitate those discussions. And also helpful in understanding the differences in the types of controls when you're talking about wind, PV, battery, and grid following versus grid forming as well. So we'll walk through a few different, just very high level types of equipment when it comes to IBRs. First one here I'll mention. Before this, like we had type 1s and types 2 wind turbines, and I'm not really going to touch on those. Those are sort of legacy equipment. I don't think there's many of them out on the system anymore these days, but those are they're fixed speed. They have a lot of various limitations in terms of ride through and voltage support and these sorts of things. So we're going to kind of pick up at type 3 when it comes to the evolution here. So type 3 is a defig, a doubly fed asynchronous generator. It's got two sort of paths to the system connection. It's got an induction generator that has a direct stator connection to the grid, and it's also got a back-to-back peak power electronics converter that's has a capacitor on the DC leg. So it's got these sort of like two connections to the system. It's a bit of a unique device in that it has some machine attributes because of the direct induction generator connection, but it also has a whole lot of IBR aspects to it as well. These types of machines, the reason this configuration exists is because the rotor side converter, which is here, big leg here. This is okay. I'm just gonna put. So this rotor side converter here is going to be basically we in the world, of course, we have wind speeds that are variable, and to get to extract as much energy as we can out of for a given wind speed, we need to sort of keep the speed of the wind turbine, basically keeping a constant ratio between the wind speed and the turbine speed here. It's at a high level. That's what we're trying to do here, and that's why this configuration exists. Is because we have this rotor side converter, which can really drive the speed of the wind turbine to extract the most energy out of the wind. And we also have this grid side converter here, which we can use to control the reactive power out of the turbine here. So we have independent control over active and reactive power out of this device, which is something that you didn't have from the previous generations. Next one here is the full converter, and so in this figure here, so this is a Type 4 wind turbine. You can see starting from the mechanical side, we have this wind turbine connected to typically a synchronous unit here, and then through a back-to-back converter here. And the benefit of this scheme, of course, is that this whole circuit on the left side, I guess your left side as well, can basically run at whatever optimal frequency you need to extract as much power out of the wind as possible. The frequency can be different in the system on the left compared to the grid frequency, of course. So again, this is very useful for extracting as much power out of the wind. Of course, you get independent control over active and reactive power with this configuration, because you have all the power going through this converter that's connected on the grid side here. And a PV inverter in many ways is similar to this type 4 in terms of the grid interface that you see. It's a full converter. It's got instead of this rotor side converter or turbine side converter, it doesn't have that, of course. It's got PV panels and maybe has some DC-DC controllers there as well. But in terms of the grid impact, it's generally a similar sort of interface that you have with a PV inverter. And a battery inverter is, again, similar to PV, except that it's got even fewer constraints on the DC side. You can very quickly take power out of the DC side and inject power into the DC side, and the voltage is not going to change a whole lot on the battery, because for transients, the state of charge typically doesn't change very much on a battery. So just at a high level, the kind of typical, I'll say typical here with parentheses, because every manufacturer is going to have their own sort of like takes on how they could do the controls here. But in a sort of a generic sense, the control structure, the grid following control structure, typically looks something like this. So if we start on the let's start on the right hand side here. At the end of this control structure, we're going to get a voltage references. I'm going to show this in DQ domain here. This is sort of a typical way of controlling a grid following device. So you get a DQ voltage reference, which the inverter is then going to try and impose on the system at its terminals. Before we get there, we have inner current controls, and this is this section here. And again, we're split up on the D axis and the Q axis, so we can have independent control over several output variables based on these controls. And this is a very fast controller. Generally, this is going to be going to have a bandwidth often in the could be in the low kilohertz sort of range. And it has to be extremely fast, because the output of the inverter the output current needs to be tightly regulated. The IGBTs or whatever switching element is used, they're heavily current constrained. You can very easily damage the equipment if you push too much current out of them. So these control loops are intentionally very fast in order to tightly regulate the current output of the device. So there's important limiters and things like that here, and there's all sorts of nuances we can get into there. But just at a high level, keep this in mind here, that we have at the end of this chain of control, we're going to have very fast current control loops, and these current control loops are not typically not modeled in your phasor domain positive sequence dynamic controllers, right? Main reason being is that the time constants associated with these current controllers are too small to accurately model in the phasor domain program. So in your phasor domain, you're going to have all this stuff on the left that's going to produce a current reference, and that current reference is going to be exact. That exact current reference is going to be basically imposed on the grid. It's going to just directly inject that without sort of this detailed control loop. So this is a major distinction between the phasor domain and your EMT dynamic models. So looking out to the left of the inner, we have what we call the outer controls, and these are operating at a slower time constants. So generally you'll have inside the inverter, you'll have an active power controller and a reactive power controller that is creating the references for the current control loop, and that's sort of this interface. This dotted line represents that sort of error term going between the two control loops here. And these outer controls are going to be running quite a bit slower than your inner controls. more on this, can be milliseconds to seconds, kind of depending on what specific attribute is being controlled. Again, we have PI controllers, we have limiters, we have some filtering happening as well. And as inputs to our PI controller, to our PQ controllers or outer controllers, we'll have some PPC inputs, right? So your plant controller will say, hey, for a given voltage deviation that I'm seeing at the POI, I want you to inject this much reactive power. And there'll be, their own set of very, relatively speaking here, very slow controls compared to these inverter controls. On the active power side here, the PPC on the, is it can run in different ways, but a lot of the time on the active power side, you're just controlling the DC voltage actually, right? So going back to that full converter example, you can imagine the wind turbine is injecting power into the DC bus, and that power has to we want that power to get out to the system. If you don't extract that power out of the DC bus, the voltage is going to rise very quickly. So in the control space, we can just control that DC voltage to some reference, and that'll be sort of the control mechanism for taking that power from the turbine side out into the grid through the DC side, and similar thing for PV and as well. But then, if a plant is curtailed, then this switches from voltage. It can switch from voltage control to a power reference control rather. And on the Q axis here, typically reactive power control. So the PPC, as I said, is going to be sending reactive power commands to the inverters to get a certain amount of Q output at the POI. So if we look kind of more at how these voltages are sort of actually imposed on the system, we have basically two different ways of representing it. The interface itself. So what I'm showing on the screen here is an average source representation. And I know a lot of you are going to be familiar with this, but just as a refresher here, an average source representation, we have effectively voltage sources that are the interface to the grid. And what we do is we take these voltage references here that were generated on the previous control diagram. We'll take them and feed them through, we'll have to convert them from DQ to ABC domain. And we'll do that by putting it through a DQ to ABC transformation. And in order to do that, you need an angle for that transformation. And you get that angle from a phase lock loop. So a phase lock loop is going to be tracking the terminal voltage to determine, try to figure out what the phase of that of the system is. Okay, and I'll explain really briefly why that's the angle or the phase here is really important, right? So we know that let's say we have this really cartoonish representation, oversimplification, but it drives the point home of let's say like an inverter and some impedance, and then some infinite bus here, some V grid, right? And this Z grid or ZG here just represents all the impedance between those points, basically between the inverter and the system. The current between these 2 points, if we're looking at it in the phasor diagram here on the right, so we have a voltage, IBR, and a V grid, and the current is basically just going to be the difference between VG and IBR divided by the grid impedance. So the angle of that voltage that's being created at the inverter terminals is going to determine how much current is going to flow into the system, right? So this is all perfectly fine in steady state. I think this makes a lot of sense. Now, let's say we have a transient on the system such that this grid phasor moves somewhere else, right? So it moves right here. It moves like, can't draw. Let's say it moves somewhere over here. right? This is a very extreme example, but let's say it moves somewhere over here. Now, immediately, if we assume that that inverter angle isn't changing, we get a huge increase in the amount of current, right? We had this before, this little one here, and then once this angle changes, now we are looking at more like this. So it's a huge jump in current if we don't do anything. So that's why these current controllers have to be very fast, right? So the current controller will basically change this. Effectively, it'll move this this VIBR phasor over this way so that you can again have the difference between these two phasors to be small so that you limit the amount of current. This is an important concept to understand, especially when you start talking about grid forming versus grid following, which I'm not sure if we're going to get there in this course, but it helps to understand that. And you know, as you can imagine, there's a few controllers that play into, there's a few critical parts of the controller that play into how this voltage phasor moves. That's the phase lock loop and the intercurrent control loops, both of which you can't really represent in phasor domain properly. So you can get an approximation of PLL dynamics, but there is no, because the PLL actually you know, it looks at instantaneous voltages and it tries to track them. You won't have instantaneous voltages in phasor domain. So, you know, these key dynamics in terms of like stabilizing the inverter output for movements in the system are effectively, you can only really model them in EMT. So it's just something to keep in mind. And also this angle that the PLL produces, it gets used in a lot of places, not just in this conversion from DQ to ABC, but also when you're measuring the current output. In this previous one, in this current controller, right, we had two parts to this current controller, of course, the reference, ID and IQ reference, but also the measurement here, the ID and IQ measurement on the system. And you generally want to make sure those are, you know, you're understanding those measurements on references on the same base, on the same, in terms of the same angle. So that PLL angle is extremely important. And we can also, you know, this also gives an idea when we start talking about like weak systems that this, you know, this controller works very well when this grid angle is not particularly influenced by the amount of current that we're injecting onto the system. When the grid angle is severely influenced by the amount of current, that's when we can start running into weak system issues. And that's when we can say the grid is no longer stiff because that system angle, it starts to vary a lot based on the amount of current. So you can run into these situations where if you have some overshoot on your current control loop, you can maybe move the system angle, you know, substantially to a place where you want to now move your inverter angle in the other direction, and you basically get these phasors eventually just oscillating out of phase with each other, and which is kind of the underlying mechanism for weak grid instability as well. So if we look at the full IGBT representation, now we no longer have those voltage sources are gone, and now they're replaced with actual switching elements here. And these switching elements, we are sending fire impulses to them. So instead of taking those ABC voltages that we got from our DQ to ABC transformation, we can, you know, in an average model, we just impose those directly on the system and assume no switching basically, or no switching dynamics. Now, we can also represent this phenomena with you know, actually putting the switches into the model. And for that, we, you know, in our representation that we're showing here, we have a you know, plus DC and a minus DC bus here. And these are our ABC quantities here, our ABC connection points here. And we can use these switches to impose a certain a waveform onto the system. The way that gets done is through this control topology here. So this is, you know, PWM, effectively pulse width modulation. So you can see that we have a phase lock loop here generating an angle. and that part is all the same. There's no difference in that part of the model. And now when we go down here where we were previously taking those let me go back to the highlighter where we were previously taking, not highlighter. Where we were previously taking those DQ voltage references and putting them through the transformation and then putting those directly into the average source. We can now take those, and instead of putting those right on the average source, they now generate the reference signal for our PWM. So in our PWM, we have a reference signal, which is this waveform here. You can imagine that's your, let's say 60 hertz waveform here, and we have a carrier signal, which is this triangle waveform here, which will be at a much higher frequency. This will be definitely in the kilohertz, and depending on the inverter, this could be in the in the tens of kilohertz or higher. And so this is happening much faster, and you need a smaller simulation time step to be able to model the switching. But effectively, at the end of this, you have a comparator that just compares whether the carrier is above or below the reference here, and that'll determine your firing pulses that are sent to the switches. Okay, so that's some of the fundamentals of the sort of like detailed controls here, in terms of how most grid following IBRs are implemented. At least, again, there's all sorts of nuances and OEM specific aspects to this control here, just to get you an idea of how this works for most equipment. So we can take a very quick look at a generic model here of an IBR plant. And here we have a, this is it. Again, I'm trying to be, as sort of agnostic as we can here. And this course isn't really intended to teach you how to use a specific tool, let's say. So you could definitely, show this in any EMT platform. But here we're showing it in PSCAD. And what we have is a solar inverter. Inside the solar inverter, there's a transformer, which is, sometimes the transformer is outside the sort of inverter page module, let's say. Sometimes it's inside, so don't be too nervous if you don't see. Oh, sorry about that. Sorry, folks, I'm sharing the wrong screen here. All right, let's try this part again. So in this example here, we have a PV inverter on the right here, connected to a high section here, which is your collector system, through a main power transformer, and then connected to some sort of system equivalent here. I have a test grid block, which we'll talk about a little bit later. And then we also have a plant controller over here. And the plant controller is measuring some quantities at the POI, and it has some references, and it is creating P and Q commands that are being passed to the inverter. And there's some delays and some sampling associated with the plant controller as well. These PQ commands are being accepted into the inverter model. And most of the models that you look at in EMT look kind of like this. As we said, you might have multiple plant controllers. You might have a hybrid plant that has multiple resources. So it can definitely get a lot more complicated, but at its sort of like simplest, it'll look something like this. And we can look inside of the PV inverter here. This is just a generic model. It doesn't represent any specific manufacturer or anything like that. But if we look at, going down from the main connection point here, we have a breaker, we have some metering, we have an inverter transformer with a scaling component on it, so we can represent, various numbers of inverters. And we have some filtering that's happening here. which is very, every inverter has this as well. The filter itself can look different. It can be in different configurations. And then way on the right side, we have an average source representation here. And we have some DC representation here. And we basically program in some equations into the model here to dictate how the power transfers through from DC side to AC side. So we can use that to sort of approximate what would happen on the DC side as well. Also in this model, you'll see, go to the right here, you can see that there's protection settings. Too dizzy. There's some protection settings here, which is typically what you would see in models as well. This is a relatively small number of protection settings. Most real inverters have a huge number of protection settings, which are much greater number than what's shown here. But again, this is just a generic model that we're looking at. So you can see under voltage protection and blocking, over voltage trip settings, under frequency and over frequency. And then we have a series of control blocks here, which really have inside of this inverter controls. This is really the heart of it, or one aspect of the heart of it. Let's say this has those outer control loops, those PQ control loops, and those inner current control loops are inside of this block here. And we'll also have a phase lock loop block down here, inside of here. In an actual, OEM supplied model, all this stuff would be basically black blocks into one block that you can't look into at all. And that's for to basically hide the IP from whoever has this model and to protect the IP of the manufacturers. So that's just a really brief overview of what an EMT IBR plant model might look like. There is also a series of protection flags here, which are really useful to look at when you're trying to figure out why something goes wrong. And if we go up one page again, it's the other aspect of the model that's also really valuable to keep an eye on is the outputs of the plant controller, these PQ commands. If you want to understand why either the plant controller or why the inverter is not doing what it's supposed to be doing, it's useful to look at these commands here as well. All right, I'm going to switch bases now and move back into model testing and design evaluation and pick off a little bit where Alex left off. Before I do that, any questions on IBR controls or this generic model that we're looking at? Yep.
Well, data can be correctly presented in the phase limit simulations. I read some articles, things like that, saying that you represent it even in a simplistic way, it could help in weak grids.
Yeah, so there's been a lot of work done in that domain, right? Trying to get some PLL representation into the sort of web generic models. They've definitely shown reasonable comparisons in generic models under some grid conditions. I guess in our shop, I don't know if we've seen enough evidence that would say, hey, you can use this to represent the, even approximate the performance in a weak grid, in an actual weak grid. There's definitely been a lot of good work into it. And I think in certain instances, those models are going to be useful for you for sure. But there's all sorts of, but that's basically for generic models, right? Once you go into the user-defined models, those approximations may or may not hold, I would say. And really, once we're that invested in the behavior of a device in a weak system, we should probably just be doing an EMT study and do your best to try and get those detailed models from the manufacturers wherever possible. But that's not to say that those models might not be, those phasor domain models might not be useful and approximate enough in certain circumstances. For example, when you don't have an EMT model, right? Or if it's far away from your study area or these sorts of things.
I have a question.
Yeah, please go ahead.
So yesterday, I think Alex mentioned, actually, you guys recommended to use average model instead of detailed model, right? I think when you, one of your slide you mentioned, you recommend average model over the detailed model in most of the studies. Yeah, but you also, like pick the PPT, one of the slide you showed was also the average model, right? Well, one, but you know, some of the, so they state clearly, they want model all the way to LGBT.
Yeah, like, so the switching model is always going to be more accurate. In the sense that it has the switching. Those accuracy differences are not necessarily going to be important to the type of study that you're doing. I would say often they're not. Most of the time they're not. So the caveat there is like, so you can ask for a switching model for every single IBR plant in your system, but the switching frequencies can be really high, right? And you might need like a really small time step to simulate those switching frequencies, even with all the simulation tricks that we can do, interpolation and things like that. We can still have instances where the time step can be really making your model so slow that it's not usable in your system.
That's one of my questions. Like when utility took a developed model into the plug into their bigger system, they're gonna have dozens of renewable. If you have all those carrier wave, it's like 30K hertz or whatever, 66,000 hertz. It's gonna take forever to just initialize. I wonder why those requirements are put there in the first place. Like, do you think the new actually 2802 gonna remove that and instead of that, I just recommended to use average model?
I don't think there's anything got to you about switching models.
I'm not, yeah,
And I'm not sure. Are there, I don't think there are requirements for a switching model.
so like, yeah, like, I mean, from like an electronics perspective, we say you could bring either model for basically most studies. And we have a strong caveat that if the switching frequency is really high, and that means you have to run a small simulation time step, then we'll just use the average model. You know, it's quite easy to set up a model to do both, right? For you to be able to switch between them inside the model.
Even got a question about, like, you know, most of the PV model, battery model, they just model the DC side as a DC source. Constant source, you don't need to worry about any of those. But we got requests asking about it to be modeled as a PV panel, all the cells in China and Syria. So,
Right. Well, okay, so that, I mean, that's a bit of a different question.
yeah,
but
and I know, I'm just saying, like, the level of the details, right?
Yeah, it varies
It's
and
not necessary for two though, that's.
so on the switching side, I would say it's not a bad idea for just asking for both models. And most manufacturers are going to be able to supply both models. Like, you know, you can make this switch happen pretty easily inside the model. It would probably take a modeling engineer only maybe a couple days to take an average model and create a switching model, or the other way around. It might be very fast as well. Might be less time than that. There's also been some exercises where people have actually taken like and you know, done it themselves if it's open box enough to do that, which I don't really recommend, but it's been done before. Now the DC side thing is a bit of a different question because there's you can't really study like a lot of DC side phenomena if you have a fixed voltage source there. So a lot of these events that we looked at in Odessa, a lot of the tripping events are related to like DC side phenomena, right? Like DC under voltage, DC overcurrent, DC over voltage, these types of things. And you won't see that with a constant DC source. So I think it's valid for you know, transmission planners to ask for models that have those DC side aspects modeled in some amount of detail. the degree of detail, I think we can talk about those nuances and, but, you know, our recommendation is to try and collect models that don't have fixed DC sources for PV, for example, or battery.
Not like you guys are pushing to make those.
Well, we're pushing, like, from, you know, from our perspective, we're interested in getting accurate models that are able to represent the type of events that we're actually seeing on the system, right? If you give us models that are not capable of representing some DC phenomena that we've seen happen in the system, then we'll start to ask these types of questions, right? So where these model requirements are evolving based on what we're seeing on the system. They're not static, like, and they change every couple of years based on what we see on the system, right? We're still maturing, right, Zach? So I think it's a really good question, though. Right, so now switching a little bit to EMT model intake and model testing. I think Alex basically covered everything here. You know, why we want to collect and have good quality EMT models. You need these types of models in order to do studies, whether that's a design evaluation study or whether it's a detailed system study. And you really don't have that many opportunities to collect these models. Once the project goes COD, it's very difficult to get these models. So even if you're not planning on doing a study with the model today, you should still, my recommendation is to still collect that model if possible. And I think we can make a reasonable case that that's allowed under for 2023, where they say, you know, if you're doing a study, collect the model. Design evaluation, I think it's reasonable to say that that is a study. So I think that's reasonable to do even for plants that you're not you don't have a system study scope for that facility. So again, some of the requirements here, some of the typical requirements that we see in EMT model requirements is the model. The main one is accuracy, right? Is it detailed enough? Is it correct? Does it represent the actual field performance? Is it validated? We can ask for a validation report. We can go through all those nuances that Alex mentioned in that validation bit. We also want to make sure that the model is usable. Can we actually use it in our study? Like, is the simulation time step reasonable to be compatible with our larger system models? Is it locked to a specific time step that's going to cause a problem for other models? These sorts of things. And site specific, does it represent the equipment being used, or is it parameterized accordingly, etc. The other big piece of model requirements, again, model requirements or model intake is sort of a process here. The other big piece that has got a lot of emphasis in recent years is performance testing. So, you know, is the plant likely to conform with basic performance needs of the system? Whether those requirements are coming from 2100 or whether those requirements are whatever the transmission owner or the ISO has for that facility. We can do some level of performance testing in this process that is separate from a detailed system study. We also have checks and documentation. And this process may also include benchmarking between EMT and phasor domain models, and it may also include testing of specific capabilities, such as grid forming, which is, or, you know, if you look at the ERCOT advanced grid support requirements, this is another one there. So on the performance testing aspect of the model intake, this is going to include a lot of, you know, can include a wide range of things. So fault ride through and recovery, voltage and frequency ride through, phase jump, rock off ride through, voltage frequency support, weak system performance testing, and testing specific capability. And the system model that is typically used for this, it doesn't know it's saying this is the only type of system model that needs to be used for this. We can, you know, there's been lots of proposals to use more sophisticated test grids, let's say. But is basically here to model your IBR plant. connected to your, your point of connection here. And then you have some equivalent grid impedance here, and then an infinite source on the other side of the grid impedance. And this grid impedance may be variable. Maybe you're changing it to represent different system strengths and things like that. And then, of course, you can apply a variety of faults. So this plot here on the right is an example of where we take this sort of simple test system, and we apply a fault, and we change the SCR, change the grid strength, and we do that consecutively. And we can see where the performance of this plant sort of falls apart in terms of the weak system performance. So just a couple notes on some of the terminology and timelines when we're talking about model intake, just to give a bit of context here. And this is not a comprehensive list. There's been a lot of other timeline, like things that happen in this timeline, which are relevant to this, but I'm just want to highlight a couple ones. So late 2000s to present is, late 2000s is when electronics first posted our model requirements document. And that was really in response to there being no requirements out there by anyone at the time. And early versions of our requirements focused primarily on the model accuracy and usability aspects, with some basic performance tests added later. And when I say basic performance tests, I mean this was really quite basic. This was basically checking whether the plant rides through a 3-line to ground fault for some SCR of 3, let's say, in our simple test grid. And the reason we started doing the basic performance stuff is because, well, when we didn't do that, we would just take the model. Okay, it looks accurate enough from what we can tell. We put it in our system study, and the first thing we do to it is apply a fault, of course, and then it immediately trips, or has some sort of other basic performance problem. So just to sort of make that process much more efficient, we would, as soon as we receive the model, we apply some basic tests to it to make sure it has some basic level of performance. Now, jumping ahead to today, we have the latest model requirements version is revision 13, which was posted in 25 and has a performance test that roughly match the proposed 2000.2 SAPRU 3 tests. So this is roughly 50 tests or so that we're sort of proposing in our model requirements. Now, in between there, like in 2020, ERCOT released their model quality testing requirements. They had model accuracy requirements before this as well, but this is when they started putting more emphasis on the model quality testing aspect. And then this is accuracy emphasis plus some ERCOT-specific performance requirements that you'll see in their MQT. So that's really where the term MQT started being used in 2020. And then after that, of course, we had 2100 in 2022. IEEE 2100 does have an Appendix G, which highlights EMT dynamic modeling requirements, is the name of the appendix, which includes a lot of the accuracy and usability features that were taken mostly from the electronics model requirements, but also had been adopted by a lot of other entities at that point. And now looking into the terminology that's in 2000.2, so there we're distinguishing between design evaluation and MQT in the standard. So design evaluation, we can test whether plant meets some IEEE 2800 plant level performance requirements. And an MQT is also sort of defined in the document, which is more of a preliminary check on model accuracy and basic performance. So these are somewhat separate terms in the standard, but a lot of folks will use these terms actually quite interchangeably and will take aspects of one with another and kind of put them into one big process. So, so just a note there, these terms will get confusing in a lot of processes and things like that, but in a lot of places they kind of mean the same thing. And of course, there's been many others along the way. So I guess here I'll just note the one. I guess some of the questions have been actually in kind of in reference to this. So the design evaluation test plant against many aspects of the requirements in 2800, it doesn't guarantee that the plant is going to be stable on the actual system, right? So again, this is mostly like electronics perspective here, but in my perspective, it shouldn't, just because it passes design evaluation doesn't mean that you don't need to do an EMT interconnection study if you know that the system is going to be weak or that it's serious compensator or any other type of things that might trigger a detailed EMT study. That being said, there's a lot of plants on the system that aren't going to be triggered for a detailed study. And the only study they're ever going to get is the design evaluation. So we should place some emphasis on the design evaluation in that sense. And it's helpful for us to be, I think, somewhat conservative in the assumptions around the design evaluation. If that plant never gets a study in the system, which includes all other detailed IBRs, et cetera, you'll still get some level of, you have some degree of confidence in the performance of the plant from the design evaluation, even without a detailed study. System dependent, I'll say. Yeah, in today's landscape, there's a whole bunch of other requirements. Many entities in the US and around the world have these MQT and design evaluation processes. Some are much more onerous than others, let's say. We'll take I think a quick walkthrough through the electronics model requirements here. There's a lot of footnotes to these requirements, I'll say, that aren't in the document in the presentation here, and they're important footnotes. So I would definitely recommend if you're interested in more detail, have a look at the document, and it should hopefully help answer some more questions. But let's step through them kind of quickly here. So A, represent the full detailed intercontrol loops of the power electronics. So those intercontrol loops, those PLLs, those PQ controller loops, we want those to be modeled and we want them to match the actual equipment on site. And the note here, that models which embed the actual hardware code are currently widespread, and this is the required type of model. And this is electronics requirement, so we can say whatever we want. We're saying, please we're asking for models that actually use the real code inside of the model. So we don't want to see generic models. And there's a whole kind of conversation there. There's a difference between a generic model and there's steps in between, let's say, a fully generic model and a model that has the actual hardware code in it. You can take just like the building blocks, let's say from a block diagram of an inverter, and you can try to recreate those block diagrams inside of the EMT tool to build that plant model. But there's lots of nuances in how those controls are actually written inside of the controller that you might miss a lot of detail there. For example, an integration, like an integrator, you can do integration a number of different ways. You can apply limits in a number of different ways. If you're just recreating those inside of the EMT software, you're just relying on however that's implemented inside of the EMT solver of the tool that you're using. Whereas in the actual equipment, that might be done in a different way. Those limits might be applied in a different way. The way the integration is done might be different. And you could say, oh, those are minor differences, but why would we even bother? But when we do these detailed grid studies, and especially like weak system studies and subsynchronous controller interaction studies, these details actually really make a big difference. And you might get the wrong answer out of your study if your model is not accurate. So the next one, represent all control features pertinent to the type of study being done. So if you're, obviously like a plant controller is like a external voltage controller or plant controller, customized phase lock loops, ride-through controllers, SSCI damping controllers, basically not just the intercontrol loops, but all the other stuff that's in the actual equipment. We want that inside the inverter model as well. represent plant level controls. So the PPC is one that's gotten a lot of attention over the last couple of years, let's say, and I think rightly so. So the history on PPC modeling is kind of interesting. Like when I started electronics, let's say we didn't care a whole lot about PPC modeling, to be honest. We often just didn't include PPC models. If it was there, fine. If it wasn't, we didn't really think too much about it because in the back of our heads, we always thought that they were slow devices that weren't going to have a lot of impact in the time frame that we're looking at in the studies. And then we started, these are actually going to make a big difference when we're looking at certain types of voltage recovery and things like that in the system. So, okay, let's put them in. And then immediately we just got flooded with generic PPC models, just REPC type PPC models. And that was sort of the status quo for a little while. And, in more recent years, we realized, okay, those generic plant controllers and models were actually very wrong, particularly in terms of their reaction time. They were linear models that responded immediately to a voltage deviation on the system. In reality, especially at that point, the models were, in the system, they were responding like it could be 500 milliseconds to a second before the plant controller would start doing anything. So really, we were better off with not modeling the plant controllers at that point. But this is a learning process, right? So we're adapting as we go here. So specifically, we're calling out those communication delays, transport delays, measurement delays due to bus communication like Modbus, sample and hold logic, and really any other type of delay that may influence the plant response in the time frame of study is what we're asking for. D represent all pertinent electrical and mechanical configurations, filters, specialized transformers like grounding transformers. We want those in the model. Mechanical features, gearboxes, pitch controllers, and then to the point about DC side, PV panel dynamics, DC controllers, and the caveat here, they must be modeled if they impact electrical performance within the time frame and electrical purview of the study. So if you don't put them in, you really, in the end here, any control or dynamic feature which may influence behavior in the simulation period, which are not represented or which are approximately should be clearly identified. So if you're not including some of these features, it might be reasonable to do so, but you have to sort of like convince us that it is reasonable to exclude those types of controllers. And I would say in a lot of cases, depending on what we're talking about, but we might say that's unacceptable. That's a valid answer that you might get from a T or an ISO. Have all pertinent protection models for balanced and unbalanced fault conditions. So, and very important, individual phase and RMS. This is again a distinction from phase domain where the phase protection is basically not in the models, can't really be modeled. DC side protection, overcurrent protection, any protection which can influence dynamic behavior, same sort of thing. Be configured to match expected site-specific settings. Default parameters are not appropriate unless these will match the configuration and installed equipment. Talked a lot about that already. Now, a couple notes on model usability. We also, of course, want to be able to use these models effectively in studies. So we want to have controller hardware options, which are pertinent to the type of study accessible to the user. For example, if you're doing a reactive power coordination study or something like that, which is not, maybe EMT tool isn't the best tool for it. But for example, if you're doing that type of study, you would need access to the droops as a study engineer, to the voltage droop characteristics and the dead bands and things like that. And other types of, if the point of the study is to tune, element X in the controls, then that should be made available to you. Diagnostic flags should be made available as well to aid in the analysis. Be accurate when running at a simulation time step of 10 microseconds or higher. 10 microseconds here is kind of chosen as what kind of striking a balance between a time step that you would be able to represent a switching model on, I'll say a lot of inverters like that aren't using an extremely high switching frequency. With 10 microseconds, you can still reasonably represent switching on a lot of equipment. But also, still being able to run that model in a reasonable amount of time, so it doesn't slow down your whole simulation a lot, right? So there's nuances there in terms of switching, and there's a lot of footnotes and things like that which you can look at. Operate at a range of simulation time step. This is if somebody gives you a model that says you can only use it with a time step of 10 microseconds, and another person gives you a model that says you have to use 16.667 or something like that. Then if those are both like inside the same plant or in neighboring plants, those inverter models, then you're going to have compatibility issues if you try to run them in the same EMT model in EMT case, assuming that your EMT case doesn't have capability to model time steps, like individual time steps for individual parts of the case, let's say, which some EMT tools do. But yeah, even in that case, we should have the ability to represent a range of time steps. And then documentation and sample implementation. And a test case. This is actually quite helpful. Like in some instances, we just receive a model that's just like in a library, let's say in the EMT tool, and doesn't have like an actual working case attached to it. So sometimes we just take that model and we put it in just some generic test system, and it doesn't work. So we don't have any reference for a working case for this inverter. So we have to send it back right away. It's really helpful to have some working example so that you can sort of back check and say, okay, I took the model from this case and put it into this case, and it stopped working, but I don't know why. You don't have any, like, without a working test case to begin with, you can't really pinpoint like which action you did that somehow broke the case. So sort of an implementation detail, but it's important. Identification mechanism for configuration. So this is, you want to have some sort of information inside the model that says, okay, this is the control code is this version, the firmware is this version, right? And ideally, you can map that back to actual equipment. If it's just some manufacturer might just over and over again release the model that appears to be the same from the outside with the same .lib names or whatever, same .dll names, and no sort of like versioning baked into there, you can be kind of left into the dark as to what version of the code or what version of the model you're working with. So that can be quite important. Accept external reference variables. You don't want to have like hard-coded voltage references or hard-coded active power references inside the model that you as a user can't change, right? Somewhat self-explanatory, but you'd be surprised. Be capable of initializing itself. So if you give it some set of initial conditions, you should expect the model to come up to those initial conditions by itself. You shouldn't need to pause the simulation at exactly 0.2 seconds and change the value of some variable inside the simulation and then click run and have it get there. That the model should be capable of doing that itself. Again, self-explanatory, but a lot of these things have like backstories of like, many situations where we didn't get this and it was extremely annoying and it was really delayed the study a lot and caused a lot of problems. So these are all rooted out of years of experience, let's say. Ability to scale the plant capacity. So you want to be able to, let's say, study it in a situation where only some of the inverters are online or at a lower power dispatch, right? So that's important as well.
For the last one, I think there's two different approaches. That one is, you can, for the OEM model, you can just directly set the rating and the number of inverters. It's going to automatically do the filter and everything for you, right? So you can do whatever. But I saw some other recommendation. They just modeled like one IGBT level, maybe like 2 kVAR, kVA or something. Then they use the interface transformer in PSCAD just use that way. Basically, they scale up the BNI on the other side. So is there any limitation on the second representation, you think?
So that, yeah, like scaling is is an important thing that we can talk about, and this will change based on the platform, I think, to some degree. Ideally, I think basically all inverters now, maybe with some exceptions, but a lot of them are coming in as like a single wind turbine or a single inverter, and they take care of the scaling externally. That approach is much preferred, in my opinion.
Yeah, I do feel the second one gonna cost some numerical issue because the value of those will be so small and, right?
Yep, so the scaling can be done improperly for sure. Like if you can set up the scaling so that again, this is very program specific, let's say, but you can set up the scaling improperly so that, there's this like scaling component. I don't know who developed it. I don't think that's a master library component, but you set a small X value. It doesn't tell you, but it adds a lot of B to actually implement that scaling, to create a traveling wave interface there, to do the scaling. So you don't need to do that anymore, at least in the more recent versions of all these tools. You can just do like ideal scaling, where just more at the EMT algorithm level, it'll apply a scaling factor, and you don't even really need a scaling transformer, or any sort of external current injection or anything like that. You can just, most of these tools will just have a way to, I'll just show you. I'll just show you the tool. So this current scaling component here, again, we're looking at PSCAD, but I think other tools have this as well, or something synonymous to this. This is an ideal scaling, so there's no like extra charging or extra reactance or anything added here. So on the left side here, you can have like an individual inverter transformer and an individual inverter, and it'll just scale it up by whatever number you enter here in an ideal manner.
This is better.
This is the best.
Better one.
This is the best one. Yeah. There's ways of doing it which are really bad.
Yeah,
Let's say
there's some e-tron module that you transformer and.
it's pretty good too, but this is the best that I would recommend right now.
Thanks.
Yep.
Quickly, Henri, for EMTP, is it the same scaling that you'd see in this tool? Same photoplastic? Okay. Just to say that this is similar amongst all the major tools.
Right. Okay. Alex, when do we want to break for lunch? It's 12 now. It's a good time. Okay. All right.